That's the title. And so I'll just thank I've worked with lots of people in this area of compressed sensing, and some of these people are the ones who've got me into this area. And so I should thank Ben Adcock. I think he's here. Oh, there he is. Good friend of mine. And I've been working with one of his postdocs, Simone. This is one of my former postdocs and a student of Albert Cohen. Adela Shakifa, one of my current students, Joseph Dawes. My former students, Nick Dexter, who currently works for for Ben, and one of my close collaborators, Huang Tran. Okay, so what are we going to talk about today? So this is the motivation. This is the same motivation I give if I was talking about UQ type problems, but in the high dimensional setting, I think this fits. So what I'm really interested in is the solution of high dimensional parameterized PDEs. And you can think of them as I have a set of D parameters that pass through some model, where I have some operator that can be linear or nonlinear, acts on some coefficients, and I want to compute some quantity of interest with respect to those parameters. Okay, I'm going to do this with some polynomial approximation, in which I'll induce compressed sensing, but we'll come to that in a second. For now, just think of the parameters as just in some d-dimensional hypercube, and the assumptions I'll have is very simple, that I'm living in this d-dimensional hypercube, and if they're stochastic, they have some joint density, and I'll take samples according to that density. And I want this map to be well-defined in analytics. So if this is a PDE problem, this will enforce some assumptions on the coefficients. This could be coefficients enforcing functions, so I need continuity, coercivity, analyticity to guarantee existence and uniqueness. Okay? And this is a challenge that shows up in a lot of problems, not just in UQ, but in a lot of different problems that my group at Oak Ridge works on. And I'll just mention a couple: scientific medical imaging, of course, uncertainty quantification, optimal control, parameter identification. One we spent a lot of time on is kinetic plasma equations, many-body Schrodinger equations, et cetera, et cetera. And so the question that we ask ourselves is, in the high-dimensional setting, how do we handle all these parameters and all the resulting data? So data here you can think of as the result of the simulation. It could also come from an experiment in the case of, say, medical imaging or scientific imaging. And so one solution to this problem is, well, we can build better hardware that can store and transmit more data. And even though I sit at a place that, half my time at least, that has the world's most powerful supercomputer, certainly there are limitations that exist to this solution. The alternative, which is the one that I advocate for, is to design better inefficient compression methods. And in other words, methods that compress the map without having to acquire the entire solution map a priori. Okay? Instead, just probe at it and then recover the solution. All right? And so what am I going to talk about today? So today's talk, I've been told I have 30 minutes precisely. So I'm very bad with time. So you're going to probably have to pull me off at some point. But what we're going to look at is we want to query the solution, or we want to take a query of the input data, approximate the solution map, and we want to have accuracy that's comparable to the best approximation. And in this case, I'm going to say best polynomial approximation. The best polynomial approximation, or at least the sharpest available estimates in this area, exists in this paper we put out in 2016 in Numerical. And so that's kind of what we're going after, and I'll say a little bit about that in a second. And so I'm going to break this talk into 3 parts. I guess now I have 8 minutes per part. So novel theoretical advancements in compressed sensing. I'll show you a little bit about this new chaining argument we came up with for proving the optimal estimate of the number of samples, in this case for L1. I'll show you then how to precisely choose weights for weighted L1 to overcome the curse of dimensionality. And then in more computational side of the house, I'll show you how we can use this weighted L1 procedure for recovering high-dimensional functions, even PDEs. And I'll throw something in on images at the end related to wavelets. And the last thing I'll do is joint sparse signals, or reconstructing joint sparse signals from data. And joint sparsity is not a new thing, but in the context of PDEs it is. And so I'm going to show you a mixed norm-based L1 regularizer that exploits both energy and sparsity to reconstruct the parameterized solution in both physical and the parameter domain. And under the hood there, we also proved a very nice result, which I'll mention at some point, on strong convergence for forward backward splitting in this case where you have joint signals whose length is infinite. Okay? All right, so here's the basic setting of where I like to live, at least in this talk. So I'll be in a multidimensional setting, so I have a multi-index, and I'm going to approximate the solution U by, in this case, orthogonal polynomials. I'll live in a bounded orthonormal system. We're doing a lot of work these days, as it seems like every approximation theory group, in neural networks, which I might mention at the end. But regardless, we want to approximate a solution of the following form. Why? Because we can take advantage of smoothness or sparsity, and we can usually prove something about increased convergence to the quasi-Monte Carlo schemes. The challenge for us is that the computation of these coefficients in high dimensions requires the cardinality, or the number of samples, to be at least, or even the number of computations, at least on the order of the cardinality of the set. And the efficiency depends heavily on how one chooses the index set, okay, as you all know in hyperbolic cross approximation. The true coefficient in the case that I have a complex value function, well, this is just a complex vector, but in the more general setting, when I have a PD solution, these coefficients are, say, Hilbert value functions. Okay, this is where the complication could come in when you try to extend compressed sensing results. And like I said, I'll assume this is an orthonormal basis. So this is, all of you know this well, and this is where I'm going to separate between a linear approach and nonlinear approaches. And so in the standard case, what people called back in the day polynomial chaos or orthogonal approximation with polynomials, one would impose a lower set a priori, say a tensor product, total degree, even a hyperbolic cross, or even a Smolyak space in, say, the context of sparse grids. And they would impose this lower set, that is, I have no holes, and then do their approximation scheme after the fact. So they would say, well, I alleviate the curse dimensionality because I have a set that grows, say, sub-exponentially with respect to dimension. And on the other hand, things that we're more interested in is that instead of a priori imposing this set, we're going to construct it based on the S most effective indices to guarantee the best S term approximation. And you immediately might ask me why I don't use Stechkin, and I think most of you in the room know it's not a sharp estimate. And the paper I mentioned earlier, we have a very sharp upper bound of how this error decays with respect to the best S term approximation, and I'll show you how sharp it is right now. So here's just a 4D example. So this is the rate we want to go after. And so I just take a four-dimensional elliptic problem where I have its analytic function, and this is the region of analyticity. So this is the Bernstein ellipse diameter. And so I just do a Taylor approximation. In this case, it's just affine expansion. And the asymptotic rate, using the estimate I just showed you, decays like a sub-exponential. In fact, the best rate, using, say, an Earhart polynomial, decays like this black line here. And you can see that our rate that we impose is almost right on top. This is theoretical, of course. Now, just to show you a comparison, this line right here would be Monte Carlo, and these various blue lines are your Stechkin estimates. Okay, just to show you how not sharp Stechkin is in this case. And also, if you impose the Stechkin estimate, which was used by Cohen, DeVore, and Schwab, then you get something that, when you compute the coefficients, blows up in this order P as well as in the dimension. Okay, and that's really bad. Even though you can claim that you get exponential rates or you get algebraic rates of convergence. All right. So now let's move to compressed sensing and then show you how we want to reconstruct solutions that guarantee those best S term rates. So as many people know in this room, this was initially developed for signal processing, and the idea is that we want to recover signals from underdetermined systems. And by sparsity, I just mean I have a few active coefficients. And I'll use the phrase S sparse vector to just mean a vector with the most S non-zero entries. Okay? And in this context, one might say, well, how would I recover with some sparsity-induced norm? Obviously, L0 is optimal, but NP hard to solve, so we can impose, say, L2, we can impose L1, or even, say, non-convex schemes. We've done some theory on non-convex schemes in this setting, but in general, what I'm going to impose now is that I want an L1 scheme where the optimal solution or the minimal solution is this corner, okay? In this case. And I'll also be interested in uniform recovery results, and that is success with high probability for all S sparse vectors. All right. So in this setting of polynomial approximation now in high D, I'll assume we're given some index set. It can be far from optimal. I want to recover a function of the following type. And to generate the compressed sensing setting, I'll take M samples according to that measure rho. Okay, this is just of the data. I'll then form a matrix, which is nothing more than the basis functions evaluated at the points. And then the data is nothing more than the solution evaluated at those random points. The coefficient then solves the linear system. And we know that if we want to construct an approximation comparable to the best S term, then this requires the samples on the cardinality on the order of S, and therefore this is underdetermined. Okay? So we can use greedy thresholding optimization. We're going to use we're going to use optimization in the L1 sense. And this is all I'm saying here is that, and I'll go through this quickly, that the sparsest solution to that problem is the L0 problem, which is NP hard. We can move to L2 and generate overdetermined systems. And instead, we're going to use a convex relaxation in the L1 sense that we want to minimize vectors in L1 subject to that constraint. Okay, so uniform recovery in this setting is usually guaranteed through something called the restricted isometry property. And that is that I have matrices, normalized matrices that satisfy the following upper and lower bounds. And I'm just going through this quickly because I'll run out of time. That one can show that the RIP implies a null space property, which is necessary and sufficient condition for recovery. And so therefore, if I have an RIP estimate, then I can bound the solution or the error in L1 by the best S term. And the challenge is, how do you estimate the optimal number of samples to guarantee an RIP? Okay, and there's been a lot of work done on this since the first papers on compressed sensing. And so the goal then when we took over and got involved in this was to establish a reduced complexity with respect to compressed sensing. The first thing we weren't happy with is these log factors, so we wanted to try to reduce those. There's also a constraint on this mutual coherence. In other words, usually we take a uniform bound of the basis functions, but as say you have a Chebyshev basis, this grows like 2 to the d. Legendre, it grows like the cardinality of the index set, and even the precondition of Legendre is still not so good. And the other thing we wanted to do was to optimize the cardinality of the underlying index set, and this is where your hyperbolic cross will come in. So the first thing we proved was, and this is in a math comp paper, that a matrix that satisfies the RIP, if the number of samples grows like theta squared S, then there's a log squared. So the previous result coming out of these papers of Bergon and friends showed that this was a log cube. We are able to drop that by a log factor, and I'll sketch the proof for you to show you. So as of today, this is the best estimate. We think we can improve it even more, but I don't really care about it that much anymore. I think we've gone far enough with this. And this proof is valid for any bounded orthonormal system. And I'll show you how this chaining argument works just quickly. So the idea in proving these things related to the sample complexity of compressed sensing is you want to prove that if you have a random matrix of size n by n, then with high probability that when I apply it to a sparse vector C, that it's approximated by C in L2. Okay? And the strategy is similar to previous papers that have been around for a while, and that is that for randomly sampled points, I want to prove with high probability that this sum approximates this integral. And so we do this. I won't go through these details. I'll just show you that we construct a class of discrete approximations to this function. We then use a tail estimate to prove with high probability that this is true. And then we use this estimate, or to prove this estimate, we apply a union bound to show with high probability that this is true over this discrete class of this approximation to C. Now the idea though is that you need to control the cardinality of this set, and you do this by a covering argument. Okay? If you use the straightforward extension of what's done in Bergon, which is shown up in a few papers, then your problem is that your cardinality will scale like the covering number of this, and he uses a pseudo metric of the following type. The problem is that this will grow exponentially in D in this case. So what we did was we thought of ways to ignore the values that blow this up, and instead we come up with a distance function, not necessarily a pseudo metric, and show that this function agrees everywhere except for the values of y that blow this thing up. These are only a small fraction. In fact, you can show their size measures 0, and their elimination has no effect on the RIP, and the result is the covering number is reduced by a log and doesn't depend on dimension. Anyways, this is all the details are in a very long math comp paper. Okay, and the last thing we wanted to also show is that how do we reduce the dependence on this mutual coherence? and I also want to improve the underlying index set. So as I pointed out, primarily we were focused on parameterized PD solutions, and typically the best S term can be defined on an approximate lower set. So the idea was, let's reconstruct solutions that are comparable to a best lower approximation. In other words, a best approximation by S terms forced on a lower set. The reason for this is that you get less demanding approximation schemes, of course. You can show that they're about equivalent, and then you can choose the enriched set to be hyperbolic cross, because the union of all lower sets is a hyperbolic cross, and then we can exploit estimates that have previously existed on counting the cardinality of these sets. Okay, put this in the context though. So how we did this was we introduced something we call the lower RRP. So what you'll see in other papers is terms like they'll have bounds that rely on best S term approximation, but they're really best KS term approximation, where KS is defined in a similar way. In other words, RKS is a soup of the bounds of these basis functions, assuming the set is lower in cardinality S. And then we introduced a RIP estimate, or a RIP requirement, that says now that I want this to be true for all z satisfying under K tilde, the soup of z is bounded by this K of S. And this is really a subclass of the set of all z S-sparse vectors whose soup is lower. And you can also think of this lower RIP as a very special case of this weighted RIP that was introduced by Rahut and Ward in 15, the difference being that the lower RIP induces a very specific weight. In fact, it says that one should take the norm of the basis in L infinity. And coincidentally, this is why Ben and I got involved with each other. Oh, that sounded a little creepy. But anyways, that he also came up with the same requirement in the non-uniform recovery case in a series of 2 very nice papers. And then later we showed this to be optimal. Okay. And under this setting, then one can say the following statement, that if I have a matrix A, normalized matrix, then as long as M is greater than, you can see now I've replaced everybody by K of S, and this satisfies the lower RRP with the similar delta. Okay. And here are some very specific examples you might be interested in. So let's look at the case of a Chebyshev or Legendre basis. In this case, I can take estimates from the Shikifa, Cohen, DeVore, lots of people, Schwab, Timponi, Nobili, 25 author paper that shows that in the Chebyshev case, they can bound this term by S to the log 3 over log 2, or in the Legendre case by S squared. We use those estimates for K of S, and then we use the bounds on the hyperbolic cross, and I can put this all back together and show you that this will scale like I said, S to the log 3 over log 2 with this log squared, and then you get something linear in D. Okay? And that's nice because now you've reduced in high D, you've reduced the approximation scheme to something that's essentially linear in the dimension. All right? To guarantee now the best S term approximation. Now, the weighted L1 to actually implement this or use it, it's quite straightforward. You choose a specific weight. I have my random sampling matrix. If I have a tail estimate, I'll use it. I then solve this minimization problem, which is the L1 minimization subject to that constraint. All right, so let's do 2 quick examples. How much more time I got? 10 more minutes?
10 more minutes.
Good. All right. Halfway through. Plus epsilon. Okay. All right. So let's do some simple cases, just functions in multi-D. This is where we started. And so let's take an 8-dimensional function of the following type. This is the coefficients computed using Legendre approximation, and then I sort them. Well, someone sorts them. And then, so this is just telling you this is the coefficients and sorted. And then I'll show you if we plot the error. So this is the error in expectation against the normalized sampling, so normalized by the cardinality of the set. And I'll use just standard L1. This is the approximation. I'll increase the weight. So this is about half of the L infinity norm of the basis. This is the L infinity norm of the basis. So you can see it increases the convergence slightly, and eventually it just stops. And you don't get anything by increasing it further than just the L infinity norm. Okay? And this is 8D, so you take the same function as 16D, look at the coefficients again, and similar results. So here's the L1, I can increase it eventually. You'll see that even the L infinity norm, which we tell you to use, turns out to be the best, regardless of how much you increase it. All right, so those are simple examples, just functions. So let's move to PDEs, and I'll say a little bit about this. and how this is related to joint sparsity. So I call this energy norm regularization for recovering PD solutions, and the reason is that if you think about what you're doing in compressed sensing, you're solving a complex problem in the sense that you have realizations of the function in, say, or complex valued realizations of the functions. And if you want to extend that to the PD setting, it's not so trivial in the sense that you can think of everything I just told you as nothing more than I take one realization of the PDE at a physical point, don't worry about time, in your physical domain. I then evaluate it at a bunch of random points, and then I solve a whole bunch of these L1 problems, okay? And this is essentially what's been done in several papers. In other words, you can get either a functional of the solution U, or you get the evaluation of the global solution U at a point. Okay, so now if you want to recover the function everywhere, you either have to interpolate this thing or do some piecewise approximation to this thing on your full domain. All right, and that's all I say here. So if I want to recover the global coefficients on the whole domain, then I need some interpolation scheme. The other issue is that here you require a tail estimate pointwise, which you don't really have. You usually have a global tail estimate. And the other thing is in the parameterized setting, typically all of these ideas exploit some decay of the coefficients, but that's a global decay of the coefficient, not a pointwise. And so what we're going to do is we're going to change the definition of the norm. I'm now going to mix it with an LP norm with a Hilbert norm and rewrite the following norm on the coefficient. So I'll have a mixed norm of V. You can think of this as H1 mixed with LP, and it's nothing more than a sum of the H or the V norm to the 1 over P. Okay, and everything I'm saying here is in this archive, and it's currently in review. Okay, so here's a very simple example. I won't go through the details of this, or I'll run out of time. Just say you have an elliptic problem with a coefficient A, which is parameterized. You can think of this as affine expansions, non-affine, nonlinear expansions. The solution of this problem is analytic. It's been shown in several papers. We showed it in a very general setting in that Numerical paper, regardless of the type of noise that one has or the type of expansion of the coefficient. And then this is kind of the point, is that if I look at compressed sensing pointwise versus looking at the global approximation. So if I just take 3 random points in your physical domain, I look at the coefficients of the PDE, and I plot those coefficients. Now this is an expansion in, say, Legendre basis. Okay, and then I plot that decay. You can see that even though the rate is the same, it's certainly not the same decay. So one would need a separate compressed sensing algorithm evaluated at every single point in your physical domain. Okay? Whereas when I mix the norm, then what I do is I just have one recovery. It's just a much bigger problem. Of course, what I'm telling you is that I'm mixing the norm a priori, so I have matrices of vectors, but those vectors are not discretized, so they're of infinite length. Okay? They're Hilbert-valued solutions sitting in the matrix. So this is where the joint sparsity comes from, but each vector in the matrix is a Hilbert-value function. Okay? Okay, and that's what I'm going to say now. So that's why I say regularize, then discretize. So some people might say, well, discretize, this is an argument even in the Feynman community. So what I'm going to use is this convex relaxation, and I'm going to first regularize by mixing the norm. So I have your standard constraint with this regularizer, which is now mixed with my Hilbert space. And then what I'm really, under the hood, what's going on is as follows. I'm then expanding the coefficients in, say, an orthonormal basis of the following type. So then each C nu corresponds to a vector in C1 by n. So it's these big long guys. Okay? And then if I want to recover the global solution, it's determined by a matrix in Cn by n. This is the natural numbers, okay, of the following type. And then I can write this norm, this mixed LQ norm, as a norm mixed with little l2. Okay? And that's all I'm showing you here. And I can, so therefore I'll interchange those the rest of the talk. So you can think of the solution in, say, h1 to the n as a matrix in Cn by n. Okay? And now the recovery looks very similar, except now I have this over sets, I'll call them R, so these are the vectors of the solution, and therefore I have to recover these vectors simultaneously. Okay? And after we started this, we realized, well, this is a special case of joint sparse recovery, but now we have vectors of infinite length, and there was really not any theory in that setting. There was some theory in other settings, which I'll go through. So in this case, one could show the following. We introduce something we'll call the VRIP, which is just a mixed RIP with this Hilbert space. And then you can prove that if you have a matrix that satisfies the VRIP, you can take the same constant as in the standard case. Nothing changed with the sampling matrix. The sampling complexity is also the same, and then you can prove that, say, in L2 for the PDE, you can bound by the best approximation. You pull a square root, you can't help that. But anyways, so you still recover the best S-term approximation. Now globally, though, globally. All right. Just to say a little bit about how you actually implement this, the standard procedure for implementing this is, say, Bregman or forward iterations, or forward-backward iterations, and then we had to, say, mix them, which is what we did here. In the case of the forward-backward iterations, we established a strong convergence, in this case when you have the infinite, even in the infinite dimensional setting. So there was the case of the finite dimensional setting was done by Daubechies a few years back, also by Combetz. And then we extended all that to the infinite dimensional case. In this, I'll show you this paper later. There was also a finite convergence setting done by Halian and Zhang in 2008. Okay, so let's see how it works in practice. I'll take the standard problem that we proposed 10 years ago, elliptic problem. You have this exponential covariance function. This is just a Fourier expansion of the coefficient. Here's the basis function, or the eigenvalues and the eigenfunctions. And then we're going to play with the dimension and correlation length a little bit, just to show you this, how this converges. So this is the case if I did a decoupled recovery and then I do a piecewise interpolation to the basis to recover the solution globally. So this is the convergence of that versus this global joint sparsity convergence. You can see it's dramatically improved. And this is just telling you the decay of the coefficient. So this is a D equals 100 dimensional problem with a pretty small correlation length of 1/4. Here you're only moving the total degree. It's a total degree approximation, not using the hyperbolic cross, where the cardinality is around 5,000. And I have a very simple finite element mesh under the hood. Okay, and then how does this thing compare to the classic stuff in this setting, Monte Carlo, sparse grids, etc.? So here's the Monte Carlo convergence. Here's the rate, 1/2 m to the minus 1/2. And this is the expectation, and this is the standard deviation. Same D equals 100 correlation length of 1/4. So you can see that I also plot the degrees of freedom of a projection scheme, even though we can't quite compute it properly, but we do it. And then this is the sparse grid. I can only get 2 evaluations, but it does a pretty good job here. For the expectation, the variance, the compressed sensing result starts to do a little bit better. The point here is this is not weighted in any sense. This is just standard L1 right now. And then we can go to a little bit harder problem. Why is this a little bit harder? Because this is so in this case there's a lot of anisotropy, which is why the sparse grid can take advantage of it. And in this case there's not so much, so the L1 case should do pretty good. Very small correlation length, just 17 dimensions, but all active. And now you can see that even in expectation and in standard deviation, it does much better job. And then if I go a little bit further, go back to that problem, which I wasn't able to do so well on, and I introduced the weighted L1 case to this. So this is again D equals 100, correlation length of 1/4. And now you can see that even with the same sampling complexity as Monte Carlo, I can get rates much faster than sparse grids, for example, by taking advantage of this weighted L1. Okay, okay, so I'll finish up there and say a few things about extensions of this and what we're up to these days. So I showed you some certified recovery guarantees for fighting the curse dimensionality with weighted L1. Showed you the sampling complexity for compressed sensing. And just to point out that, we rely heavily on smoothness of the function and polynomial approximation, but we can do this on lower dimensional cases. We've been working on image painting with this idea of weighted L1. We're now comparing this against this reweighted L1 idea, and we're using wavelets on closed lower trees. So I'll give you an example. This is just a cartoon image. I have this, I want to do it, this is the unweighted L1 recovery versus the weighted L1 recovery, where I'm only using 4% sampling of the image. All right, but do a little bit more than just cartoons. We can take a textured image, for example, look at unweighted L1 versus our weighted L1. And like I said, we're comparing this also to reweighted L1 ideas. This is only using 10% of the samples. And here's one using flamingos. One of my students has some affinity with flamingos. But the real reason is you want to be able to recover things like even their little tiny legs. If you look at this unweighted recovery, not so good, versus this weighted recovery does a pretty good job with only 8% of the samples. And even you can go a little bit further and even look at scientific data where you have an image, say, weather patterns one wants to recover using weighted L1 unweighted L1 interpolation versus this weighted L1 interpolation. So this, again, using wavelets on closed lower trees. Just to show you that this idea can be extended to other things. This is going to come out in an IEEE signal processing paper. And the other thing is I talked about was this mixed norm stuff. We're recovering jointly the solution to PDEs. I didn't show you anything about the proof of this forward-backward splitting, but we have proved the strong convergence, and we'd like to extend this to Bregman and split Bregman, and I think we'll get it soon. And the other thing I just want to say is this is something we've done very recently, which is beyond just weighted L1. So in weighted L1, we're trying to fight the fact that when one wants to prove sufficient condition for recovery of in compressed sensing, we have this estimate, which is m times this theta squared s. This is a mutual coherence, and this is shown in several previous papers. The idea that we have decided to pursue is that we combine this something called the restricted eigenvalue condition, which the statisticians realized a long time ago, with sharp envelope bounds of, say, for example, Legendre system, and then one can show that this restricted eigenvalue condition, which I guess is well known, it implies a robust null space property, so the upper bound of the RIP is not necessary. And what we're actually doing is, if you think about it, in the normal case, when we look at all the, say, Legendre polynomials, the bound we take is the uniform bound, and what we're now doing is saying, let's change, rather than a uniform bound, let's have a bound that depends on the function, okay? And we can estimate the sample complexity by going back through our chaining arguments. So in other words, I define a set of the following way, and then I'll count the covering number of that set under that pseudometric I showed you earlier. And so if I go back through the logic, the covering number then involves an upper bound of the following type, okay? Here theta is the bound of all the Legendre polynomials, for example. If I take theta as a function of y just to be the soup like we did earlier, then this estimate scales like the following, and consequently you can pull out a k squared s times log factors, okay? If instead I exploit the envelope of the basis, now I have this function of y, of all the Legendre polynomials. The problem with that is that this function now becomes unbounded. However, with very high probability, we get sample sets where we can prove that this bound scales like the following, okay? In other words, if I defined a function z of y, which is nothing more than this function theta of y times this exponential term, then the theory also tells me how to sample, which is pretty slick. In other words, it tells me I want the preferable sets to sample is where this sum is small, and in that setting you can prove that the sampling complexity scales like the following. In other words, it scales like s squared times log factors, no k. So you've killed the mutual coherence without introducing a weight. Anyway, so this I think is pretty slick, and this is in this very recent archive paper and also in review at Foundations. Okay, and with all that, I'll just say a couple other little sneaky things we're up to. We're looking at, we've established at least a class of null space conditions for non-convex, non-separable minimizations, showing when they are at least as good as L1 at recovering exact signals. This is in this archive. It's in review. We also are working on, we almost had this, but we failed. But so we have what I'll call the first theoretical computational algorithms that are pointing towards rank-aware manifold optimization. That's in this archive paper. And very recently, we just proved the following result in a very general setting, and that is that if one wants to build a neural network in this case to approximate global polynomials, then we can tell you the number of computational units as well as depth to recover a generalized, let's say, discrete neural network and for general activation functions, and that is to recover the best polynomial approximation in high dimensions. The result says that For any S, there exists some neural network whose complexity can be bounded in the following type depending on S. That is the number of nodes and the number of levels. And then you can pull back this uniform bound. And this is telling you can get sub-exponential rates that don't depend on D. And that's almost done. And that's, I think I'll end there and take any questions. And here's a whole bunch of references and stuff I talked about.
Thank you very much for the nice talk. Questions, remarks?
You have flexibility in choosing an orthonormal basis of algebraic functions.
Yeah.
But for instance, you mentioned Chebyshev, you mentioned Legendre, but how do you decide which one to use?
I mean, in this case, we decided based on the measure. So we started with, in a PD case, we start with a coefficient who's expanded in, say, a KL type expansion with a measure. The measure is uniform, so I take Legendre.
Yeah, but again, this measure.
Yeah, I can change it. Yeah, I can change it. Well, I mean, you're getting closer to dictionary type learning, which is a little bit, maybe one more step. But yeah, I mean, in the bounded case, one could take other ones. I mean, based on the results, you should take Chebyshev. But then be careful if you use the Chebyshev polynomials with a uniform measure. But yeah.
So you emphasize the point that with this joint sparse recovery, you're looking at the infinite dimensional case, like in terms of the spatial component. But then for your experiments, I guess you spoke about the finite element basis with whatever 200 or 500 elements. So in the end, you go to finite dimensional approximation. So the question is, do you fix that beforehand?
Yeah. Even in the experiments, we regularize first, and then we do the discretization. We do exactly as I said. We don't impose the final element basis a priori. We impose an orthogonal basis, and then we do the regularization, and then we impose the final element approximation after the fact. But you're saying that eventually you end up in a finite dimensional setting? Yes. But I'm doing the regularization first before I introduce the discretization.
And the other is it's more remark. You had this plot where you changed the weight, and you said if you go beyond the L infinity norms of the functions, you don't see an improvement. I think the point is if you increase the weights, you got also error bounds in smoothness norms and not just in like L2 or something. So you wouldn't see it in these plots, but if you go to different norm of measuring the difference, if you also take into account derivatives, then you would see a difference. That's what I would expect.
But it's an analytic function, so
in terms of the approximation.
I don't see why I would see that. I don't see why at all I would see that.
Maybe for that particular example, maybe right, but in general, if you have a rougher function, then
maybe if I have a rougher function, yeah, but if I have a rougher function, then a lot of the theory falls apart because we rely on the fact that you have a smooth function.
So if you increase the weights, then it's ensured that the approximation gets smoother. So anyway,
you could continue your conversation in private with a piece of paper and
like that.
Any other questions? Oh, then let's thank the speaker again.